तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will review what we learned about eigenvalues or calculation of eigenvalues in the last lecture, and then go ahead and look at certain other ways of computing these eigenvalues and eigenvectors. The first we saw that eigenvalue problem is basically finding the solution of an equation A minus lambda I equal to 0 for a matrix of form A, as if the matrix equation A x equal to B. In a matrix equation A x equal to B, if the right hand side of this equation is 0, then how do we solve? That is where we started this eigenvalue problem, and the importance of solving equations where the right hand side of this matrix equation is 0. That is where we started the discussion on the eigenvalue problem. And we went ahead and said that we would be interested in solving equations of this form, that is A minus lambda I into x equal to 0, that is the eigenvalue equation. And we said that this kind of equations have non-trivial solutions provided the determinant of A minus lambda I is 0. That leads us to the what is called the characteristic polynomial, that is determinant of A minus lambda I equal to 0 for a matrix of the form A is the characteristic equation for the eigenvalues. So, this characteristic polynomial we learned a way of constructing this, that is using the Faddeev-Leverrier method. We saw that how to construct, given a matrix A minus lambda I, its characteristic polynomial, which is lambda n minus p n minus 1 lambda n minus 1, etc. So, we saw that this can be constructed by finding the traces of a series of matrices given by a recursion relation, starting with the fact that p n minus 1 is just the trace of the matrix A, and then we can construct matrices of A into the B n, which is B n was to start with was A itself. So, you say A into B n minus p n minus 1 I. We can construct matrices of that form and take the traces of that, and that is the traces which goes as the coefficients of this polynomial, of this characteristic polynomial. So, we saw that, and then we were wondering how to solve this equation. Now, we have the polynomial, but we have to find the roots of this polynomial. There is a polynomial in lambda. So, the roots of this polynomial are our eigenvalues. So, the eigenvalue, finding the eigenvalue, the problem of finding the eigenvalue was then that way split it into two. One is to find the characteristic polynomial, which we said for a large matrix is finding the characteristic polynomial itself is a non-trivial problem, and we said that we would use this the method we just mentioned, the Faddeev-Leverrier method for that. And then once we have the characteristic polynomial, we saw a program also in the last lecture of constructing the polynomial coefficients, and we have the characteristic polynomial. Then the question is, how do we find the roots of that characteristic polynomial? And so, now that leads us to a general problem of finding the roots of an nth order polynomial, and we said that one way to do that is use what is called the Weierstrass method. So, in the context of the eigenvalue problems, it is the solution of the characteristic polynomial or even in the more general sense, it is a solution of an nth order polynomial. It is the roots of an nth order polynomial, which is what we want to find out, or the zeros of the nth order polynomial, or an equation, and roots of an equation of this form, that something on the left hand side is equal to a0 plus a1x plus a2x square up to a n x n. So, the Weierstrass method applies a technique of this form, that is, we say that we would find the roots of this polynomial in pairs of conjugate variables. That is, we allow for the roots to be complex. Right? This nth order polynomial could have complex roots, then we would get them in pairs, such that we have the roots as complex conjugates. And that is general enough if the coefficients of this polynomial is real, then that is general enough, or that is, we do not lose anything by making this particular, taking this particular approach. So, if you want to find the roots of this polynomial, nth order polynomial in pairs, that is, we want to allow for complex roots, and then the complex roots come in conjugate pairs, and then the best method is to, and that is what Weierstrass said, is to divide this polynomial by a quadratic polynomial, or to factorize this polynomial as factorize this polynomial as a product of a quadratic polynomial multiplied by an n minus 2 order polynomial. Right? So, that is what we discussed in the last class. So, we said that Fn, that is nth order polynomial, can now be written as x squared minus rx minus s into a polynomial of order n minus 2, which is now given by bn xn minus 2 plus bn minus 1 xn minus 3 up to b2. So, then it has a, if you take an arbitrary value of r and s, then we will have a remainder to this, that is b1 x minus r plus b0. Now, the advantage of this method is that we can determine, given an r and s, we can determine this coefficients b1, bn minus 1, b2, b1, b0, etc. by a relation of this form. So, that gives us a great advantage, that, so we have the polynomial whose nth order polynomial whose coefficients were given by a_n's, and then we divided that by x squared minus rx plus s, and we got a coefficient, a polynomial of order n minus 2 or order n minus 2, whose coefficients are bn to b2. Right? So, that is given here. And then we have a remainder, which is b0 and b1, which is given by b0 into b1 into x minus r plus b0. So, that is what. So, the idea, we can, given the a_n's, we can even determine the b's. So, the question is, how do we determine r and s? So, there we said, okay, we could do a kind of an iterative approach, that is, we could say that we start with an r and s, and we will compute what the remainder is, which will be given by b1 x minus r plus b0, and then we would adjust the r and s such that the remainder is 0. So, that is the idea. So, for that, what we do is we assume this, we start with the guess value for an r and s, and we look at using the relations which we just now saw, that is, we using this relation, we could compute b0 and b1. Right. So, b1 would be a1 plus r b2 plus s b3, and b0 is a0 plus r b1 plus s b2. And we could see whether the value of b0 and b1, whether they are 0 or not. If they are not 0, then we could say that, okay, I will expand this b0 and b1 around the value r and s, which I just assumed. So, and I write b1 at r plus delta r s plus delta s as b1 plus del b1 by del r into delta r plus del b1 by del s into delta s, and similarly b0 r plus delta r s plus delta s as b0 plus del B 0 del r into delta r plus del B 0 by del s into delta s. I can write it like this, and then I would say that, okay, so the new value of B 1 r plus delta r s plus delta s at r plus delta r and s plus delta s, and B 0 at r plus delta r and s plus delta s should be 0. So, I will find the value of delta r and delta s such that this is 0. This left hand side of this equation is 0. I could find the delta r and delta s such that this is satisfied. So, that is what the approach was. So, that would lead us to an equation of this form, that del B 1 by del r into delta r plus del B 1 by delta s in del s into delta s is equal to minus B 1, and del B 1 0 by delta r into delta r del r into delta r plus del B 0 by del s into delta s is minus B 0. And this is a simple linear equation, and we can solve this by elimination immediately. So, now provided we can do that, provided we know what this derivatives are, del B 1 by del r, del B 1 by del s, del B 0 by del r, del B 0 by del s, etc. So, provided we know what these derivatives are, we can determine delta r and delta s. So, we assume an r and s, and we compute B 0 and B 1, and if they are not 0, what we do is we expand the values of B 1 and B 0 around r and s, and find out the delta r and delta s such that the new values of B 0 and B 1 are 0. So, that is what the approach is. So, when we actually expand that, of course, we keep terms only up to the first order in delta r, and hence the new value of delta r and delta s we get may not make the B 1 and B 0 as 0. Right. So, when we expanded this here, we had expanded it only up to first order in delta r and delta s. So, this value may not go to 0, even if you solve this equation, this right hand side equation with putting B 1 at r plus delta r and s plus delta s as 0. That is, if you solve this equation, the resulting delta r and delta s may not make B 1 and B 0 as 0, because we terminated it at first order. But then we could do this iteratively and then obtain values of delta r and delta s such that B 1 and B 0 are 0. So, now the question was how to determine this derivatives. Right. So, for that, Bastow showed that the way we constructed this B 1, B n minus 1, all the B n, B i's from the a's, we could use a similar method to construct the derivatives of del B 1 of the form del B 1 by del r, del B 1 by del s, etc. From the B 1's. That is, he said that, okay, we could write a recursion relation of this form, that is C n is equal to B n, C n minus 1 equal to B n minus 1 plus R C n, etc. a form, and then we could take the derivatives of del B 1 by del r and del B 1 by del s from this equation. That was the idea. Okay. So, we would get these equations as, that is, del B 1 by del r and del B 1 by del s as, as C 2, and so del B 1, for example, del B 1 by del r. So, B 1 here would be B 1 plus R C 2, right. So, del B 1 by del r will get as C 2. Okay. So, we could substitute that here, okay. C 2, C 3, C 1, C 2, etc. That is del B 1 by del r, del B 1 by del s, del B 0 by del r, del B 0 by del s from this relation. Okay. So, we have the a's and then the b's, that is, a's are the coefficients of the nth order polynomial, and b's were the coefficients of the n minus 2 order polynomial, and then we construct the c's from the b, and that is just to get us the coefficient, that is the derivatives of del B 1 by del r, del B 1 by del s, etc. So, once we have that, we can solve this equation and obtain the delta r and delta S to our satisfaction. That is satisfaction in the sense we put a tolerance for the value and then get the B1 and values, and then we get the delta R and delta S such that B1 and B0 are 0. So that is the method. Okay. So we just see an implementation of this method in this code here. So we had a set of coefficients, let's say a polynomial. Okay. Let me show you a polynomial which has a coefficients of this form. Okay, so that is the coefficients of this polynomial. Okay, we have. Okay, so that is so let me just so we will see that this is the coefficient of the x nth term. Sorry, this is the coefficients of the coefficient of the x to the power of 0 term, and this is the coefficient. The last one is the coefficient of the nth power term. So this is actually the coefficient of x to the power of 5. That is A5, and then this is a coefficient A4, A3, A2, A1, A0. So this we are solving a 5th order polynomial here. Okay. So we are solving to start with a 5th order polynomial. Okay. So whose coefficients are A5 1, okay, A4 minus 3.5, A3 2.75, A2 2.125, and A1 minus 3.875 and A0 1.85, or in short it will be x to the power 5 minus 3.5 times x to the power of 4, 2.75 times x to the power of 3, 2.125 to x to the power of 2 minus 3.875 x and 1.25 plus 1.25 equal to 0. That is what we are trying to solve. So that is a polynomial which we have. Okay. Now we are trying to factorize this polynomial and get the roots. Okay, that is what we have. So that is first this program. Okay, after I started, I defined all the appropriate variables here, all floating point, and then I opened this file which I just showed you, coefficient.data, coef.data, and then I read out all the coefficients. Using this fscanner function, I read out all the coefficients into this array A. So once I have all these coefficients, okay, so then I know the order of my polynomial from this. So n gives me the order of my polynomial. Okay, so n equal to 4 is means 0 to 4, that is 5. Okay, so then what I have to do, I have to now iterate this, right. So I have to now do this calculation here. Okay. So I have to construct, I have the AN matrices. So I have the AN arrays given by, so just now you showed that I have the polynomial AN. Okay. So that is all the A0 to A5 I had, A0, A1, A2, A3 to A5. And then from that now I need to construct the BNs. So that is the first step. So that is done here. Okay. So as long as the order of the matrix, order of the polynomial is greater than 2, I have to construct this thing. I have to continue this iteration till the order of the polynomial is 2, right. So first I take the 5th order polynomial and I divide the 5th order polynomial by x squared minus rx minus s. That is what this example we are looking at. We took a 5th order polynomial, and now I am going to divide that by x squared minus rx minus s. And then I have to construct now B5 to B2, B5, B4, B3 and B2. I have to construct that, and that is what is done here. Okay. So I put m equal to n here, and so m is the same as n here right now, that is greater than 2, and I have constructed, I use this relation, that is Bn equal to An, Bn minus 1 equal to An minus 1 plus Rbn, and Bi for I going from n minus 2 to 0 is given by Ai plus Rbi plus 1 Sbi plus 2. So that is here. Okay. So that is what this whole thing is doing, right. That is the first Bm equal to Am, and Bm minus n equal to Bm minus 1 plus Rbn, okay. And then I go and construct all the polynomials here. Okay. So, I did that, okay, for j going from m minus 2 to greater than 0, and I come out here with this polynomial, with all the b values. Okay. So, I have all the b values here. Okay. Now, once I have the b values, and then I now construct the c values, right. So, because now the next step is to find out the del b1 by del r and del b1 by del s, etc. Okay. So, that I do that by, so I know the del b1 by del r, del b1 by del s. To construct that, I need the c relation, and then I can say del b1 by del r is c2 and del b1 by del s is c3, etc. Okay. So, from this relation. So, that is what I am going to do. So, that is, so for that the c's has to be constructed, and here is the c's constructed. So, once I have the c's here, okay, so this is exactly the same as p's, but now all the b's here are replaced by a, and all the a here are replaced by b. That is what the c construction is. Right. And then I have the matrix, this 2 by 2 matrix, which is c2, c3, c1, c2. So, that matrix, and the right hand side is minus b1 minus b0, remember that, and that is what is constructed here. So, the 0 0 element is c2, the 0 1 element is c3, and the 1 0 element is c1, and the 1 1 element is c2. And then the right hand side is given by the d column vector here, and that is minus b1 and minus b0. So, I have all the matrices, and I just solve, I invert this, I solve this particular equation, that is c2 c3 matrix c2 c3 c1 c2 into delta r as delta s equal to minus b1 minus b0. That by inverting this matrix c2 c3 c1 c2 and multiplying it to b1 and b0. That is what is done here. We have seen this in the case of nonlinear function, fitting a nonlinear function to a set of data points, is exactly the same. So, we have this relation here, and now we use that particular r and s, delta r and delta s value, which you obtain by actually multiplying the inverse of this d matrix into this d matrix, this little d matrix, that is our b1 b0, and I get a delta r and delta s, and I say r equal to r plus delta r and s equal to s plus delta r. So, I just shortcutted one step here, I just straight away write delta r as an expression here. And then what is the r and s value I am getting, and what is the b0 and b1, and that step is, I just print that out here. Okay. So, this print statement prints b0, b1, r and s. Okay. So, that is what this print statement will print out. Okay. So, it will actually print out the order of my polynomial, the r value. Okay. So, you can see that here in the print statement, it will print out the order of the matrix, order of the polynomial. In that step, the r value, so the order to begin with will be 5, right, then r value, the s value, the b0, the b1. So, once we have got the b0 and b1, we go back here and check what the b0 and b1 values are. We want it to be 0. So, I given here a tolerance of 0.001. So, b0 and b1 are not 0, then it will go continue with the new value, it will continue the iteration further, right. So, it will continue the iteration till, so now the new c values will come. This actually does not change, it can be even outside this loop, this does not change, because the a's are not changed in this loop, okay, but the b's are changed. So, the new c's will come. Okay. So, and so we continue this iteration. Okay. This is a change because the r and s is changing. Okay. So, the b's will change because the r and s will change. New r and s, with the new r and s value, we will calculate the b and the c, and we will continue the iteration till, and we obtain a new delta r and delta s, and we will continue that till b0 and b1 is 0. Okay, that's the first step. So, once we have done that, we have found the solution, we have found the r and s. Okay, then what we have to do? We have to now find the solution. So, now once we have found that, we have found one factor, right. So, we have found a factor of the form x squared minus rx minus s. So, we have found the r and s value, which factorizes our nth order polynomial. to n minus 2th order polynomial multiplied by x squared minus rx minus s. So, once we have that, we know that solution of this equation straight away as r plus or minus root of r squared minus 4s divided by 2. We know the root of this equation. So, that is what we use. So, we want to just find out r squared. So, this is minus here. So, it is r squared plus 4s. So, right, we have to find out the solution of, we have found r and s, that means we have found a factor of the polynomial, that is x squared minus rx minus s equal to 0, and then the solution of that is x equal to r, right, plus or minus root of r squared plus 4s, because there is a minus sign here. So, plus 4s divided by 2. So, remember, now we have found r and s values. So, we are finding that what is the quantity r squared plus 4s is. So, r squared plus 4s can be negative, okay, because we allow for complex roots. So, when you say x squared minus rx minus s equal to 0, the roots of that quadratic equation can even be a complex number. We allow for that, be complex conjugate. Okay, so, we say r plus or minus root of r squared plus 4s by 2. Right. So, r squared plus 4s can be negative, that will give us a complex conjugate pair. So, we have to see that, since in a C program we cannot handle complex numbers that way. So, we have to first find out whether r squared plus 4s is negative or not. If it is positive, we could straight away take the root of that and write the solutions here. I have written the solutions here as r plus square root of x, where x is now, remember, is r squared plus 4s. Okay. So, r plus square root of x by 2 and r minus square root of x by 2 as my two solutions. Now, if this is negative, then we have to take the root with the other sign, that we should find the square root of minus x and add a I in front of it, right. So, that is, so then our solutions will now be r plus I square root of minus x and r minus I square root of minus x. So, we will have r. So, now once the r square plus 4s is negative, our solutions will now be r plus I square root of minus x divided by 2 and r minus I square root of minus x divided by 2. So, that is what is written here. Okay. So, now the real part is r by 2, the imaginary part is square root of minus x by 2. Okay. I will treat them separately now, since the C does not allow for complex numbers. Okay. So, r by 2 and square root of minus x by 2 and r by 2 square root of plus x by 2. So, minus x by 2, two variables, plus and minus. Okay. So, that is what I am going to print out there. Okay. So, then once we have finished that, okay, so we will then come to, we will have what we are left with, that is the quotient polynomial, right. We factorized it. Okay, we divided our nth order polynomial by x squared minus rx minus s, and now what is left with an n minus 2th order polynomial. Right. So, in this case, we had a 5th order polynomial, so we left with a 3rd order polynomial, that is a quotient polynomial. So, I print out here the coefficients of that quotient polynomial, okay, and that is will be printed out here, and that will be now, remember, aj is, so what goes as a0 of the quotient polynomial, right, would be the b2, correct. That is the way we have written our polynomial, remember. So, we have written our polynomial as this way, that is the quotient polynomial is given by this one, that is the x to the power of 0 order terms coefficient is b2. So, that is what I call a0, right, in the original polynomial. So, in the program I had to replace all the a values with now the new a values after for the quotient polynomial. So, that is a0 becomes b2, and similarly we go all the way to a3 will now be b5. So, that is what is here. So, n is now was 5 in our case. So, 5 minus 2, that is the highest power now is x cube, and the coefficient of that would be b5. So, once we have all the b's, the correct b's constructed, we can get the quotient polynomial from this, and then we can go back. So, I constructed the quotient polynomial, and then I simply go back here, okay, and I continue the process. Okay. I now reduce my order by m as m minus 2, and then you will continue that, and then I will get a new polynomial, a cubic polynomial, and again I factorize that cubic polynomial as a quadratic into a linear. So, then we find that we know the solutions of the quadratic polynomial, and we can read out the solution from the linear polynomial. That is what we do here, and we can see that here, this implementation of this. Okay, I will show you. So, you see the coefficient data, and now we will see. So, okay, so when I run this program, so first, okay, one more step which I forgot to tell you, that we have to give some initial guesses of the R and S. Okay, so that is given here. Okay, so once we have read out all the A coefficients, we have to give an initial guess for R and S. Okay, so we have an initial guess for R and S, and with that initial guess, we will go ahead and solve for the correct quadratic polynomial, that is the correct R and S value, and then we have an n minus 2th order polynomial left, and we want to factorize that. For that, we will use the newly obtained R and S as an initial guess and continue. So, we have to give only one guess. Okay, we could have a 10th order polynomial, but we have to just give one guess value for R and S, and then we will continue use that for the next lower order polynomials. That is what we are doing here. So, we had one guess for R and S to be given here, R and S, and so that's, so when you start the program, it will wait for this input. Okay, and once in the next round, after it finishes here finding the R and S values and prints out the solutions, and then when it actually goes back here, right. So when it goes back in this point equal to m minus 2, and then it goes back. Okay, so when it does that, sorry, when it goes back from here, okay, it now does not ask you for a new R and S value. Okay, the R and S value is outside this loop, but it takes whatever the R and S values obtained for the previous factorization as the guess for the next one. So that is what is here. So we start with some guess value, let us say minus 1 and minus 1. I given minus 1 and minus 1. So then it will, so now it is printing out the order of the polynomial, which is 5. I have given minus s as minus 1 as the starting value for R and S, but it has computed the new R and new S, which is minus 644 and S is 0.138, but the B zeros are far from being 0, right. So B0 is 11 and B1 is minus 10. Okay, so obviously my guess was pretty bad. Okay, so it goes back and then computes with the new R and S as the guess, again delta R and delta S, it compute a new R and S. So that turns out to be minus 0.5 and 0.4, and the B0 is reduced to 2.1 and B1 as minus 1.80. It is again still far from 0, so it continues the iteration, okay, and then finally comes to B1 0 and B0 0. Okay. So it converges pretty fast, and then it has gone to R as minus 0.5 and S as plus 0.5. So that is the R and S value for this. So we have one factor, that is x squared plus half x minus half as one factor, right. That is R is minus half, S is plus half, and the corresponding solutions are x equal to half and x equal to minus 1. X squared plus half x minus half equal to 0, or 2x squared minus x plus 1 equal to 0. So x equal to half and x equal to minus 1 are solutions. So then we have now left with an m equal to 3 polynomial, right. That is what we are left with. The coefficients of that are, the x cube term is 1. Remember, the x cube term's coefficient is the coefficient of the x to the power of 5 term earlier. So x cube term is 1, and so we have a polynomial which is left as x cube minus 4x squared plus 5.25 x minus 2.5. That's a polynomial which is left. So now I start with R equal to minus 0.5, S equal to plus 0.5 as the initial guesses, and I compute the new R and S values from the iteration. Again, you can see that the B0 and B1s are pretty bad to begin with, and then it converges to so you can see it converges to B0 equal to 0, the B0 equal to 0 0 0 0 2 1 and B1 equal to 0 0 0 0 5, which is much less than the tolerance I had given. I given it as 0.001 as tolerance. So I got a new set of R and S values, R equal to 2 and S equal to minus 1.25. So now we have a new polynomial, a new factor, that is x squared minus 2x plus 1.25 equal to 0. So that is the solution, we have to find. Now it turns out that here r squared plus 4s, r squared is 4, 4s is 5, minus 5. So r squared plus 4s is negative. So our roots are now complex numbers. So one root is 1 plus half I, and other root is 1 minus half I, obviously because they are complex conjugates. And we have a quotient polynomial which is now linear, which is x minus 2 or 1 minus 1.999984, which is 2. So x minus 2 equal to 0, or x equal to 2 is the next solution. So we found all the roots of this polynomial, right? We found one root as 2 and one as 1 plus half I, and other as 1 minus half I, and we found earlier root as half and minus 1. So half, minus 1, 1 plus half I, 1 minus half I, and 2 are the different polynomials, different values of the different roots which you obtain from this. So we have all the eigenvalues. So that's one method of computing the eigenvalues. Okay. So there are other ways of doing this. Maybe depending upon the problem, we will have to choose what's the fastest method. Okay. So we'll look at some more methods. Okay. So we just, to summarize what we just saw, is that we computed R and S for each of the polynomials, and we looked at the quotient polynomial till it is quadratic or cubic. Okay. Or linear, I should say. Okay, so if it's linear, we could just write the last solution as x equal to minus s by r. That's what we done. Okay, and if it's whatever the quadratic polynomial which we get as a factor, we just solve that and obtain the solutions. Okay, so then we said that this also we briefly mentioned in the last class that we could. This is not the only way to compute eigenvalues and eigenvectors. We could use what's called a power method. So in the power method, we use the fact that the eigenvectors form what's called a complete basis. That means that given any vector, okay, so if you have an n by n matrix, given any vector, column vector, n column vector, you can write that as a linear combination of the eigenvectors. So any arbitrary vector v, I have given a v as an arbitrary vector here. So any arbitrary vector can be written as a linear combination of the eigenvectors. Let us say x1, x2, x3 up to xn are the eigenvectors. Each of them are column vectors. So x1, x2, x3 up to xn are the column vectors, which are the eigenvectors of the n by n matrix A. Let's say. So we now have an idea what it is means eigenvectors and eigenvalues are. So let us say these are the eigenvectors of those matrices of the matrix A, and then any arbitrary vector I can write as a linear combination of this coefficient of these vectors x1, x2, xn. Remember, each of them are column vectors. This is a fact, and I can use this fact to construct the eigenvalues and eigenvectors. So let us say lambda 1, lambda 2 up to lambda n are my eigenvalues, and I have ordered it in such a way that lambda 1 is my largest eigenvalue, and then lambda 2 is the next larger, etc. Okay. I assume that no two eigenvalues are the same, or the first or the largest eigenvalues are not the same, or no two eigenvalues are the same. I assume that, okay, or this will work only in that particular case, this power method. So an assumption I have to make is that no eigenvalues are the same. or physics terms you would say there is no degeneracy. Okay. And then we would write any arbitrary vector V0, we just take an arbitrary vector V0 and multiply it by the matrix A. Okay. So, I just take an arbitrary vector V0, which I know can be written as I just we saw Ax1 plus Ax2 plus Ax3, right. We just saw that we can write an arbitrary vector as this form. And then I multiply both sides of this by matrix A. So, I get A V0 and I call it V1. Okay. So, that V1 is now A1 into Ax1 plus A2. Remember, each of this is a column vector and this is now a n by n matrix, right. So, each of this is a column vector and this is an n by n matrix. So, I can multiply this and I get this vector V1. Then I know Ax1 by the eigenvalue equation that Ax1 is lambda x1, lambda 1 x1 and Ax2 is lambda 2 x2, right. So, I can write this equation as A1 lambda 1 x1, A2 lambda 2 x2, and An lambda n xn. And then I take this and again multiply it by A. That means I take the V1 and multiply it by A and the right hand side again by A. So, I get V2, let us say. So, V2 will be A1 lambda 1 A1 x1 Ax1 plus A2 lambda 2 Ax2 etc. And then but Ax1 is lambda 1 x1. So, V2 will be A1 lambda 1 square x1, A2 lambda 2 square x2 etc. Or if I want repeated multiplication of this matrix of this right hand side by A, I will get V to the power n as A to the power of n V naught plus A1 lambda 1 to the power n, sorry this should be n. So, if I multiply this by m times, if I multiply it by m times and then I get it as Vm as A to the power m V0 as A1 lambda 1 to the power m x1 plus A2 lambda 2 to the power m x2 x. Okay, so I multiply it by m times. And then if lambda 1 m, if lambda 1 is the largest eigenvalue in this, right, then I could take, if I take lambda 1 m out of this equation, right, I will have A1 x1 plus A2 lambda 2 by lambda 1 to the power m x2 plus A3 lambda 3 by lambda 1 to the power m etc. up to An lambda n by lambda 1 to the power m xn. But we said lambda 1 is the largest eigenvalue, and in that case lambda 2 by lambda 1 is a number which is smaller than 1 and lambda 2 by lambda 1 to the power m is almost 0, right. Any number which is less than 1 plus the power m which is a large integer is 0, right. So, for example, if the ratio between lambda 1 and lambda 2 by lambda 1 is 0.1, by the time we have multiplied this by a matrix of 4 times, it is 0.1 to the power 4, which is already a very small number. So, what is in principle, in short, what we find is that you take an arbitrary matrix V and keep multiplying it by this matrix A, and then what we end up with is that since this term will dominate everything else is negligible, we get that the result of multiplying an arbitrary vector V naught, a column vector V naught, by the matrix A m times, m being a large enough integer, is that you get on the right hand side A1 times lambda 1 to the power m x1 and everything else is 0. Okay, so, from this we can read off what the eigenvalue is and what the eigenvector is. Okay. So, if you take an arbitrary vector, multiply it by a matrix A m times, and if you normalize what you got the right hand side, that what you get is the eigenvector corresponding to the largest eigenvalue, and the factor which multiplies it is the largest eigenvalue. And we will see a implementation of this. Okay. So, this is in short I am trying to say that if I multiply it by m times, I just simply get on the right hand side the eigenvector corresponding to the largest eigenvalue. Okay, so here is a small example of that. Okay, so we will see this. That is, I have a matrix A and I want to find the eigenvalues and eigenvectors of this. So, we will first determine the highest eigenvalue or the eigenvector corresponding to the largest eigenvalue and the largest eigenvalue, and then we will see how to generalize this to get all the eigenvalues. So, first we just determine the largest eigenvalue. So, here is a matrix, look at this matrix, and then we want to find out now how to, so we start with some arbitrary matrix, arbitrary vector. Okay, so it's a 3 by 3 matrix. So, arbitrary vector, I took 1 1 1 for simplicity. So, I took 1 1 1 for simplicity and I said I multiplied that vector, that matrix by 1 1 1, okay, and I got something on the right hand side, okay, as 1.718 778 0 1.778. So, now I make the largest element on this column as 1, and so now I have what I have got was I took the matrix A multiplied by 1 1 1 and I got some number multiplied by 1 0 1. Okay, that is my first iteration. Now, what do? I multiply again this one, right. So, I multiply my vector, my matrix, I take this vector 1 0 1 and I multiply by A again. Okay, that is what I want to do. So, that is the next step. Okay, I multiply the matrix by 1 1 1. Okay, I got 1 0 1. Okay, and then I multiply 1 0 1 by the matrix again. The next step, right, iteration number 2, I multiply it by 1 0 1 and I get something new, that is 3.556 minus 3.556 3.556. That is, I make the largest element on this column vector as 1. So, I take 3.556 out and I got 1 minus 1 minus 1. Now, I multiply the matrix by 1 minus 1 1, right. So, I can each step I can compute a kind of percentage error, right. So, the previous number I got here, the eigenvalue was 1.778 and now I got 3.558. So, the error is about 50%. Okay. I could continue this iteration till this error, this percentage error, that is the deviation from the previous value with the next iteration value is very small. So, I repeat this procedure. Okay. So, now I take 1 minus 1 1 and multiply by this matrix A again, and I got now minus 7.17112 and minus 0.751 0.7. So, I guess you follow what I am doing. I just take an arbitrary, I started with an arbitrary vector multiplied by the matrix A and I got a vector here, column vector. I made the largest element in the column vector as 1, okay, and then I took that column vector and multiplied by the matrix again. Okay, so, now we are in the third iteration of that process, and we had the previous iteration we had got minus 1 minus 1 1 as the vector. We multiply that by this matrix again and I got minus 0.751 minus 0.75 minus 7.112. Okay, so, the error again, so the previous the error, that is the value obtained at this step minus the value obtained in the previous step divided by the value of this step is the percentage error. That turns out to be pretty high in the third iteration. The second iteration it was only 50%, here it is 150% because we have a change of sign. So, that as long as this is large, this is not, we are not obtained our goal, okay, but this need not decrease monotonically, that is what we just saw. And the fourth iteration we took that minus 0.751 minus 0.75 we got from the previous step and then multiplied by the matrix A and we got minus 6.223 0.7141 minus 0.714. Now, you can see that we are reaching somewhere, okay, we are reaching to values close enough. We started with minus 0.751 minus 0.75, we ended up with 0.714, 0.714 and 1. If this is truly an eigenvector, you know what we get, right. If it is truly an eigenvector, this product should give you exactly the same here with the number here, right. So, the number here would be the eigenvalue A x equal to lambda x, that is our idea in this iteration scheme. And the reason this works is because the largest eigenvalue dominates. That's what we just saw, right. So, okay, so the fifth iteration, the 714 has gone to 708, so we are almost converging. So we are converging somewhere close to 0.7. Okay, so that's the, so it's converging onto that, and eigenvalue is converging onto something like 0.06 minus 6.07. So this method, this is a way we could construct the eigenvector and the eigenvalue corresponding to the largest eigenvalue. So this is the power method. This is the demonstration of the power method. You take an arbitrary vector and keep multiplying that by the matrix A. So in each step, you normalize your vector to make the largest element in the vector as 1, and then take that vector and multiply it by the matrix again. Okay, you drop this, and then when we reach the final answer, when we actually have the correct eigenvector, and the matrix multiplied by that eigenvector should give us the eigenvalue times the eigenvector, the vector itself. That is the idea. So now you could ask the question that can we generalize this? Yes, we can generalize this. Okay, so we can generalize this to obtain even the even other eigenvalues. Okay, so that's the, for example, we can very easily see how to get the smallest eigenvalue. Okay. So now as I said that lambda 1, lambda 2, lambda n was the eigenvalues of the matrix A. Okay, and now if lambda 1, lambda 2, lambda n are the eigenvalues of the matrix A, then we know that lambda 1 inverse, lambda 2 inverse, lambda n inverse are the eigenvalues of the matrix A inverse. So let us say if lambda 1 or lambda 1 happens to be the smallest eigenvalue of the matrix A, then lambda 1 inverse would be the highest eigenvalue of the matrix A inverse. And so we could just simply find the largest eigenvalue of A inverse. That will give us the smallest eigenvalue of the inverse of that will give you the smallest eigenvalue of the matrix A. And we know the eigenvectors don't change, right. The eigenvectors of the matrix A are also the eigenvectors of the matrix A inverse. So immediately we can see that we are using the power method, we can determine, provided we can compute A inverse, which also we have learned how to do. So provided we can compute the matrix A inverse, I can compute the eigenvalues, the largest eigenvalue and the eigenvector corresponding to the largest eigenvalue, and the smallest eigenvalue and the eigenvector corresponding to the smallest eigenvalue. And in computing this matrix A inverse, we could use the Father-Leverrier method, which we learned in the last class. So now once this method, we have this idea, then we can generalize this to get all the eigenvalues, because now what we could do is we could construct this method, this matrix A minus Pi, where P is, and then new matrix B A minus Pi inverse, and construct the eigenvalue, the largest eigenvalue of this matrix B. Now let us see what does this mean. So let us write down this equation, and A minus Pi. So A is our original matrix, and we subtract some number times identity matrix from that, and we write down a matrix, an equation here. So xi is a column vector. So we have Axi minus Pxi, right? But Axi is lambda Ixi, and Pxi is Pxi, of course, and then P is now just a diagonal matrix. So this will be just simply lambda minus Pxi. So the Pi is a diagonal matrix. So this would just simply give us Pxi here. The P is a number. So lambda I minus Pxi. Okay. So we know if I construct the eigenvalues of B now, that will be lambda I minus P inverse will be the eigenvalue of that, right. So if I can have an idea about what the eigenvalues are, and then I can take a number P which is close to one of those eigenvalues and construct this new matrix B, which is A minus Pi inverse, and then the largest eigenvalue of this matrix would be something close, something where the largest eigenvalue of this B matrix would be lambda I minus P inverse, where lambda I is now the eigenvalue of the A matrix. Okay. So the only disadvantage is that we need to have an idea about where the eigenvalues are. Okay. But there again there are some some ways of guessing what the eigenvalues are. Okay. So, we could for example, just use a theorem that if you just take the diagonal elements. Okay. So, we could just say this theorem that the eigenvalues lie in circles whose centers are the diagonal elements. So, if for example, here it will be the eigenvalues of this matrix would be around 4, around 1, around minus 6, okay. And their magnitude that it will be around this value. Now, how far from 4 it will be, okay. How far from 4 is eigenvalues will be, and that distance will be given by the sum of the magnitudes of other elements in the row I. That is, this will be 4 plus or minus 2, and this will be 1 plus or minus 2, and this will be the third eigenvalue will be minus 6 plus or minus 2. So, I can use that. So, I get a P, I can choose P as 4, 1 and minus 6 and construct the new matrix as A minus 4I inverse and look at the largest eigenvalue of that. So, that will give me the eigenvalue and eigenvector which is close to 4. Right. So, in this way I can construct all the eigenvalues and all the eigenvectors. So, that is the advantage of power method. We will get both the eigenvalues and the eigenvectors simply by constructing by finding the product of a matrix with an arbitrary vector. So, that is the summary of our discussion on eigenvalues and eigenvectors, and next we will go into again solutions of nonlinear equations. We will continue from a discussion which we had on the polynomial, the roots of the polynomial. We will go and look at the solutions of other nonlinear equations, and that is what we will be discussing in the next class.